Welcome to Carolina Asks the Universe podcast. Hello everyone, I'm Carolina Dziadura from Harvard, and today I have a special guest, Anya Nugent, also from Harvard, my friend, and she was so nice, and she wanted to talk about her work today. So today we will talk about supernovae, and we will explore this topic a little bit more. This is my first podcast in English, so sorry for many mistakes. So here you are, Anya. Nice to meet you.
It's great to meet you, Carolina. I'm so happy to be here and to be talking with you on your podcast today.
Okay, so let's start with who are you? Like here, you're a postdoc, right? Working on supernovae.
Yeah.
But before you were a PhD student working a little bit more about heavy elements.
Yeah.
So let's start from your PhD a little bit. So heavy elements. Where can we find them? What are they, and where can we find them?
Yeah, so, okay, I did my PhD at Northwestern with Professor Wenfei Fong, and that group focuses on these kinds of explosions in space called short gamma ray bursts, which we know are coming from these things, neutron star mergers, which are basically these very dense, compact objects that are exerting a great amount of gravitational force on each other, and eventually that gravitational force pulls those two neutron stars into one another and smacks, and they merge together. And in that merger, we have seen evidence for the creation of heavy elements, like very heavy elements on the periodic table. So things like gold, platinum, uranium, things that we have here on Earth that are clearly very valuable, and I think a lot of us are probably wearing some jewelry with one of those elements in it, which is really fascinating.
It's really fascinating that it actually comes from the stars.
Yeah, no, it's so cool that most of what we're made of and most of what we have here on Earth is created in some kind of supernova explosion or one of these neutron star merger events. But what we were really going after is looking at so we detect like a handful of short GRBs every year. And we want to see what kind of galaxies and environments do those short GRBs occur in? Is that something similar to whatever we think created the heavy elements that we have here on Earth? And really kind of connect the two stories together. What we have here on Earth, what we can see in our solar system, does that connect to what we're seeing out in other galaxies and environments way out in the universe?
So you want to understand how these heavy elements are created in these places.
Yeah.
What other? So you said gold. What other heavy elements? You mean like everything around?
Yeah, so I think if you're looking at a periodic table, I think we typically refer to these heavy elements created through neutron star mergers as anything greater than A69. So the heaviest elements on the periodic table. It creates, it's huge nuclear reactions to get these kinds of elements. We need a lot of energy, a lot of heat, which is why they only are created in super crazy explosions like a neutron star merger.
Is it the only way to create them?
That's a really good question.
But we think for now,
so
this is the only one we actually know, like it's proven?
Yeah, so okay, it's proven in the case for neutron star mergers. So back in 2017, we saw this gravitational wave event. So basically, we have a way now with our LIGO, Virgo, Cagra detectors to be able to pick up on gravitational radiation from nearby neutron star mergers. And when I say nearby, that's like way outside of our galaxy, so this is not going to affect us, luckily. But so basically, we saw a neutron star merger happen. 2 seconds later, we saw a short gamma ray burst. And then, I think it was maybe a day or so after that, we saw evidence for the kind of explosion that creates these heavy elements. So we have it confirmed for neutron star mergers that they are, in fact, creating heavy elements. But if you can imagine, the time it takes for two stars to die is pretty long. That's 10 million years or so. And then the time it takes for two neutron stars to merge into each other to exert gravitational force to the point where they can actually smack into each other, that also takes a very, very long time. And what we know here from our solar system is that whatever created the heavy elements here had to have happened on a pretty rapid timescale, much faster than what we expect neutron star mergers to be able to occur on. So there are a lot of other theories for things that can occur on much faster timescales, but we don't have any other observational evidence of things producing these heavy elements. So for example, like core collapse supernova, when a star dies and goes supernova, that there's one theory or multiple theories for how you could get heavy elements from those kind of explosions. And many observers have gone after those events to try to see signatures of heavy elements being created. And to this day, we still have really no information or observational evidence that they can produce these heavy elements. So we don't know, and it's a really exciting avenue in astronomy right now to explore.
Explore where these heavy elements come from.
Yeah.
The funny thing you mentioned, and that always fascinates me, is like a time scale, because our time scale is like people will live like 80 years, more or less, and when sometimes astronomers say things like, "Oh, it has to be like a very short, fast event," it means usually like a few thousand years at least.
Yeah, exactly. No, so the timescales that I'm talking about are always in like the tens to hundreds of millions of years, and sometimes like a billion years or so.
So okay, so we are not able to see the creation. We are able to detect some objects in a different stadium, right? That's what you mean, and then based on that, we can see what's happening in different stadiums of like the supernovae and mergers.
So basically there's like observational signatures in the kinds of transient events, the explosions that create heavy elements, and it was very clear that the explosion that we saw following the gravitational wave event, that could have only been powered by the radioactive decay of heavy elements. And so we can look for similar signatures in other kinds of explosions to see if they're being created there. But then we also have other avenues of observational evidence where we can look at the sun, Earth, and we can see that we have heavy elements here. We can carbon date those elements to figure out like when they actually got to Earth, or we can look at how old our sun is to get an idea. We knew that the heavy elements had to be within the star-forming gas that created the sun before the sun actually formed, so that we could see them within our sun's spectrum. You can look at asteroids, for example, and you can see heavy elements there. How did they get their heavy elements? So there's a whole bunch of different avenues where we're either looking at the explosion itself to try to see signatures of what powered that explosion, and connecting that to the kind of elements that were created in that explosion, or we can just visually see this object has these elements in them, therefore something must have created those elements before that object was formed, so that it had what we can see today.
Amazing.
Yeah.
I love it. And I remember when I was young and I realized that all that we are made from comes from other stars, because in the beginning of the universe we only had like a very simple elements, and every time the stars evolved, like they created more and more elements, and now here we are, created by so many elements that didn't exist and like many years ago. Right?
Many hundreds of millions of years ago.
Exactly. So but okay, so this directly kind of connects to what you're working now as already a PhD in Harvard, and this the thing you're working on is supernovae, and maybe we should start and tell people what are supernovae and what kind of condition a star should meet in order to actually be a supernovae, because supernovae happens in the end of the life of a star, but it depends on their mass, right?
Exactly.
So we can maybe
Yeah. So shifting gears a little bit. So my work that I do now are focused on like different kinds of explosions that I was studying in my PhD thesis. So Carolina said supernovae. We're studying a whole bunch of different kinds of supernovae, and yes, there are many different kinds of supernovae. And as Carolina mentioned, this is all because different stars undergo different kinds of events at their end of their life. So the kinds of supernovae that I and our group at Harvard is most interested in are the ones that are created at the very end of a massive star's life. So massive star is, typically 8 times the mass of our sun to, I don't know, maybe like 100 times the mass of our sun or so. And they basically are so big, have so much energy, that at the very end of their life, once they're done fusing all of their hydrogen and helium, which stars are made of, they basically explode in these massive, huge explosions, which we can detect as supernovae. Now, different kinds of supernovae and stars that produce that supernovae will create different features within the supernova explosions, so they look slightly different based on the progenitor star that created them.
So based on the star, what do you mean? Like based on their mass mostly?
Based on their mass, based on was that star in a binary system or was it a single star system?
What happens? Sorry,
Yeah.
side question. What happens if you have two stars next to each other and the one dies first? What happens to the other one?
That's a good question. I think that star just stays there. I think it depends on how close those two stars are together. So if they're further apart, there's like a chance where okay, so I guess this is a good point to make. Supernova explosions are asymmetric explosions. That means that when they explode, it's not like you're getting the same amount of material pushed out at all ends of the star. There's some debris that goes off a little bit more in one direction and can impart a kick on that supernova. So there are some scenarios in which like you could have a star system in a binary where the way that the debris from the explosion goes actually pushes that binary apart and then they become single stars. Or it can push you in the other way and they can move closer together and potentially even merge together. Or you could have a scenario in which the compact object produced after that supernova explosion, which is a thing like a neutron star, a black hole, or a white dwarf, it's so dense that it can actually start like accreting matter and material from the other star in the system. And all of these create very different like explosion signatures, which is so cool.
What's explosion signature?
Just like what we detect through like the supernova explosion.
Okay.
And I think it is still like a very big question how many supernova are powered by binary interactions versus single star, like the star just exploded on its own because it was at the end of its life. And so that's actually one of the questions that like my team at Harvard is going after is like what information do we need to be able to determine was that star like did it have like a twin that it was next to that was helping power some part of the observations that we saw, or was it just on its own?
Amazing.
Yeah.
Oh, I feel like when I was young and I was looking for like astro pictures that were inspiring, I was looking a lot about some supernovae and I was very fascinated about them. And it was so amazing. I was like, wow, so like the stars, they just kind of explode.
Yeah.
And then later I learned that it mostly, the end of the life of the star depends on what mass it had, right?
Yeah.
So what happens, so we are talking about, like you said, like some range between 10 mass of sun and up to 100.
Yeah.
What happens if we have a bigger star?
Oh my God, bigger than 100?
Bigger than 100.
There's a bunch of different theories. So one idea is if a star is so massive, so okay, we assume that there's a range of end states for stars. So a star like our sun, it's like actually a pretty small star, but that's good for us because that means it's going to be around for a while. So we're not going anywhere.
Exactly. The smaller the star, the longer it lives.
Exactly.
Because it burns slower. It's
yes.
fuel.
Yeah.
Kind of, right?
Yeah. So our sun is going to eventually turn into a white dwarf. Stars that are like 8 to 50 times the mass of our sun, that's going to turn into a neutron star. Greater than that, like 50 to 100 solar masses, that will turn into a black hole. But there is a big question, what if we have stars bigger than that? First of all, how do we even get stars bigger than that? You had to be like very early on in the universe to get that massive of stars, because you basically just need like a bunch of hydrogen, which was only pure hydrogen created during the Big Bang.
So basically like a large, dense molecular cloud.
Yeah, like that just collapsed into like a massive 150 solar mass star.
Wow.
But I think like with that much mass, there's so much physics that we don't know that goes into like what actually happens when a star is that massive. But there's some ideas that the star just explodes and materials flung in every direction, and there's no end state. There's no black hole, there's no neutron star, there's no white dwarf. It's done. But there's a whole bunch of different theories, a whole bunch of different ideas for like how we get to the end states or whatever happens to those hugely massive stars. But that will be like a really big thing that people will be going after with Rubin, is can we find evidence for those kind of huge stellar explosions? Since with Rubin LSST, which we just got our first preview
launched,
of the data, it's going to be seeing so many of these supernovae, so the chance that we'll be able to find one of these super rare, very massive star explosions is going to be greater than it ever was. And so it'll be really cool to see what we find out with that.
Amazing. Well, so speaking of telescopes, what kind of data do you use for your supernovae?
Yeah, so I am like an optical near-infrared astronomer. So I take advantage of like Harvard's observatory. So I use the MMT, which is in Arizona, and they have both optical imaging and spectroscopy, as well as infrared imaging and spectroscopy, and I kind of take advantage of all of that. Plus, we have the Magellan telescope in Chile, and I use that. That's like mainly we're getting optical data, optical imaging and spectroscopy from Magellan. So a lot of like data, just that, you know, within the visible wavelength range that I'm getting.
Amazing. And Vera Rubin, how are you going? So Vera Rubin is a very new telescope. It's huge. It has the biggest CCD camera that we ever built, and it's going to scan the sky like in a completely different level than we used to do.
Yeah.
And are you going to use this data?
Oh my gosh, of course. Yes. My group was just meeting the other day to talk about all the ways in which we want to use Rubin data and the science that we're looking forward to doing. I'm so excited. And I think it was really exciting. Like this Monday, we went to like their data preview event, and it was like, you've been hearing about this instrument being built throughout our entire PhDs. Everybody's been hyping it up. Every talk that you see in astronomy that, you know, has something relevant to Rubin science will bring up how much cooler things will be once we have Rubin, and then to actually see the data, just like, it's mind-boggling how good it is. It's like that first James Webb image that we got, and you're just like, oh my God, this is gonna transform like how we do science, like the cool results that we have. I'm so looking forward to like getting my hands on Rubin data.
What would you say about the fact that I feel like we, at this point, we already reached that point a long time ago, but like at this point it's even crazier that we have so much data that like there is not enough of us as astronomers to analyze it.
Yeah.
And now with Vera Rubin, if you look at like even one picture, it's like
how, like 10 million objects
crazy.
Or something? It's insane. And that's like one image. That's not even all of the images. Yeah. It's crazy. And so I think that poses like a really unique problem for astronomers these days of like, how do we actually go about finding the objects that we're actually interested in and like sifting through all of this data to find the things that are actually relevant for our research? And so my group and a bunch of other groups in like the supernova world have been thinking about this for like years, like long before I even started my PhD, preparing for the era that is like literally soon upon us. Like I think it's going to be this fall as we're just going to be getting data dumps, and just thinking about like what do we actually need to determine if a supernova is interesting? So we're going to be detecting so many supernovae. There's a lot of them are going to be things that we've already seen before. They're not super interesting. We don't really need them to do the analysis that we're trying to do. What we're trying to go after are the super rare supernova events that teach us something different about physics, about how heavy elements are created in the universe, like something really unique and different. And we are trying to come up with ways with the data and with the knowledge that we have right now to be able to sift through all of these events, the ones that we don't care about, to find the coolest ones. But I think it's going to pose like a very interesting challenge. And I also think it's cool with this new like era of AI and like all the techniques that we're getting from that. I think that's going to help like so much with us finding like the things that we care about.
Yeah, some people say that AI will take our jobs. Are you scared of AI taking your job?
Oh my God. I hope not. So the thing is, like, I don't think so.
I don't think so. The only thing it can do, it can make our work faster, right?
Yeah.
Like for example, when as astronomers starting observing, they were very slow comparing to what we are doing now, right? They were observing by eye in the beginning, right?
Yeah.
And they were just making notes about what they see.
Yeah.
And like comparing to what techniques we have right now is just like the things that they did before. It's not even like a master thesis.
Right.
It's not even a bachelor thesis for us, because now we have so much data and we have so many possibilities to use them on our like even small laptops.
Yeah.
And now with AI, I think it will be actually a step forward to analyze all of this data that we have.
For sure.
Because we have so much data that there's not, I think like there's not even enough people in the world to analyze all of it.
Yeah, I agree.
From all of the telescopes. And also we have, for example, we also have like different techniques right now that we can go back in time and look in older images and try to apply these new techniques. Like for example, applying Gaia stellar catalog for older images, and remeasure them, and based on that we could have more information. So I believe that the only thing that AI can do for science and make it even more faster.
Yeah.
And the history of our world increases so much.
Yeah.
And I feel like science also. But I don't know where is the limit. But so far, I feel like scientists are pretty much safe.
I don't think it's smarter than us right now. It just does things faster than us. I do get worried though. I think like younger generations of people, because it's funny because I remember like having access to Google in like middle school, high school was so cool. And I remember like teachers being like, don't look up things, like use your brain. And I mean, it didn't feel like that bad at the time, but I worry now with AI, like with ChatGPT, like how that is affecting younger brains. And so I guess like, sure, like AI might not affect like the way that we do, like you and I do astronomy, but I wonder like if younger generations of people, they'll become more dependent on AI rather than using their own brains and critically thinking, and like how that might affect science in the future if like they are so heavily reliant on that technology for information rather than coming up with questions on their own or figuring out how they want to analyze data on their own. I think it's interesting to think about, like, sure, it might not affect our jobs, but it might affect the knowledge of future generations.
I feel like we need to have greater teachers that will not ban using AI, but teach students how to use it in a way that it's actually productive and it doesn't make you more stupid, right?
Yeah.
But it actually makes you smarter.
Yeah.
I feel like with AI, I was able to ask some stupid questions to AI without feeling judged.
Yeah.
And it's actually, I'm so happy that it was released after, it was released in the end of my PhD.
Yeah.
So all the work I did without AI.
Right.
And I'm really grateful for that.
Yeah.
Because I know that it's so tempting to do something
it
for
is.
you. Especially when you when you see it, it does things better than
Right.
you many times. Like
Yeah.
depends on what, of course. Like
Right.
it's not skilled enough to write our paper or PhD
No.
for us. There's no way
No.
to do a science for us. But it can give you ideas. It can to rephrase your paragraph
Right.
in a nicer way and stuff like that. So
Yeah.
powerful tool, but we will see where it will get us.
Exactly.
Are you a part also of Astro AI or you're not?
I am not. Ashley Villar, my advisor, is, and her group in general is like very heavily involved with AI techniques, and even my project right now is dealing with a little bit of machine learning, which is super cool to learn. But no, I'm not involved with Astro AI.
So, what would you like to hear for when you are a student or even like younger, I don't know, interested in astronomy basically,
Yeah.
and you're like, should I do it? Should I not? What would you tell these people?
Yeah, I mean, I feel like you go into academia because you're so passionate about like the research, and if it excites you and like I don't know, it puts a smile on your face. I feel so lucky that I get to go into work every day and feel excited about the work that I'm doing and that it brings me so much joy. I have so many friends in corporate jobs. They make like a lot of money, but their jobs are not fulfilling to them as a person. And I just think like every day how lucky I am that my job actually fulfills me. And so I think for younger people out there who are deciding what they want to do, if there's something that truly, truly fulfills you, then that's what you should go after. We don't make that much money doing astronomy, but honestly, I wouldn't have it any other way. I'd rather have this life of not making too much money and getting like feeling the happiness and fulfillment that I do than taking a job where I don't enjoy 8 hours of my day and
Yes.
yeah, make a lot more
I enjoy
money.
every minute of
Yeah.
my day.
Good.
Okay, with this positive accent, I don't know, maybe there's something you wanted to mention that we haven't, like some topic that we haven't touched or...
No, I mean, yeah, I think science and academia are a very exciting place to be in. I think this world is making it a little bit scarier, but I feel like we should, if you're excited about academia, if you're excited about science, there's always place for development. Things will get better.
Yeah, thank you so much for coming to the podcast. And I hope I will record maybe one more with you, but maybe I will be back in Poland, so maybe something remotely. Thank you so much, and thank you for listening to our podcast. It was Anya Nugent from Harvard University and me, Karolina Dziadura from Harvard University.
Thank you.